Some rules in the universe feel more like suggestions, but others, they are absolute. They dictate the flow of, well, everything, from the stars in the sky to the coffee cooling on your desk. These are the rules that explain why we can remember the past but not the future. And at the heart of it all, why coffee gets cold, why you can't unbreak an egg, is one master rule. So let's dive in. We're talking about the second law of thermodynamics.
Okay, to really get this, we first have to talk about its famous sibling, the first law of thermodynamics. You've probably heard this from before, right? Energy can't be created or destroyed, only changed from one form to another. It's all about conservation. Now, look at this slide. On the left, a book falls. Its potential energy turns into kinetic energy. Simple. That perfectly follows the first law. But here's where it gets weird. Look at the right. The first law, on its own, would totally allow for the heat energy in the book and table to spontaneously gather together and launch the book back up. The energy math works out, but we know that never, ever happens.
And that right there is the central mystery. It's not just about jumping books, Think about it. An ice cube melts in your drink, but you'll never see the drink spontaneously get warm and reform a perfect ice cube. A coffee mug shatters, but the pieces never just fly back together. From a pure energy standpoint, the first law says these things could happen, but our entire experience of reality tells us they're impossible. So, if the law of energy conservation works both ways, why does the universe have this strict one-way street? What are we missing?
Well, it turns out there is a missing rule. There's a fundamental principle that acts as the traffic cop for the universe, governing the direction of pretty much everything. It's the law that gives time its arrow.
I love this slide because it's such a simple, perfect analogy. Think of the universe as having a giant one-way valve for how things happen. It's super easy for things to flow from an organized state, let's call it state A, to a more messy, disordered state, state B. That's the book falling or the ice cube melting. But that valve just slams shut if you try to go in reverse, from the messy state B back to the neat and tidy state A. This is the whole idea behind the second law. Energy doesn't just sit there. It has a preferred direction of travel. So a good way to think about the second law is the universe's ultimate bouncer. The first law writes up a huge guest list of all the events that are mathematically possible, but the second law stands at the door and acts as a filter. It checks that list and says which of those events are actually allowed to happen. And it tells us that moving toward disorder is always allowed, but moving back toward order all on its own, that's so improbable that it's basically impossible. It's the final say on what happens in nature.
Now, this big, grand, universal law isn't just some abstract thing we talk about. It has really concrete, practical implications that engineers and scientists deal with every single day. It actually comes in two main flavors, two key statements that, deep down, are saying the exact same thing. Okay, first up is what's called the Kelvin-Planck statement. Now, I know the official wording sounds a little heavy, but the idea is actually something you already get. It's all about why you can't build a perfect engine. Imagine trying to power a boat by just sucking heat out of the ocean. This statement says, nope, can't do it. You can't just take heat from a single source and turn 100% of it into useful work without something else happening. There's always a tax you have to pay.
And this diagram shows you exactly why. A heat engine takes in heat from a hot source, right? It does some useful work, but, and this is the key, it is physically impossible for that engine to be 100% efficient. That big right X says it all. You can't turn all that heat into work. You must always dump some of that energy as waste heat into a colder place, what we call a cold sink. This is literally why cars have radiators and power plants have those giant cooling towers. It's a direct consequence of the second law.
Now for the other side of the coin, the Clausius statement. If the first one was about engines, this one is about something we see every single day, how heat moves. It just says that you can't have a process where the only thing that happens is heat moving from a cold thing to a hot thing. To put it simply, heat doesn't flow uphill by itself.
And this slide nails it. Heat just doesn't spontaneously flow from a cold place to a hot place. Your cold soda doesn't get colder by magically warming up the room around it. It's always the other way around. To force heat to go against the flow, which is exactly what your refrigerator or AC unit does, you have to do work. You have to plug it in. That electricity provides the energy needed to pump the heat from the cold inside of your fridge to the warmer air of your kitchen.
And here is the truly brilliant part. These are not two different laws. They're just two different ways of looking at the exact same fundamental truth. They are physically equivalent. It's been proven that if you could somehow build a machine that violates one statement, you could use that machine to build another one that violates the other. They're a package deal. They either stand together or they fall together. So, we've established that things only go one way. But that just brings up an even deeper question. What's the actual physical reason? What's happening on a microscopic level that stops things from just happening in reverse? I mean, just think about these examples here. We've never seen a room get colder because all its heat decided to flow back into a hot kettle. We've never seen the exhaust from a car magically separate itself back into clean air and fuel. And we've definitely never seen a gas that has filled a whole room suddenly decide to squeeze itself back into one tiny corner. The fact is, nature loves to spread things out, to mix, to diffuse, and it absolutely forbids those things from undoing themselves.
Okay, so we've got it. Things don't run backwards. But why? What is the actual physical mechanism going on with all those atoms and molecules that drives this relentless one-way street? What is actually pushing everything to mix and spread out all the time? It really boils down to two main things. First, on the left, you see something moving away from what we call a non-equilibrium state. Just imagine all the air molecules in your room suddenly crammed into one corner. That's a very organized but very unstable state. The moment they can, they're going to rush to fill the whole room to reach a more stable, messy equilibrium. And the second driver, on the right, is dissipation. That's just a fancy word for things like friction or electrical resistance that turn useful, organized energy into disorganized heat. Every single real-world process has this kind of energy tax, and it's what makes them impossible to perfectly reverse.
All right, so if all real processes are irreversible because of this stuff, scientists came up with a really clever tool to figure out the absolute limits of what we can do, and that's the idea of a perfectly reversible process.
So, to understand the limits of our real world, we first have to imagine a perfect one. That's where this idea of a reversible process comes in. It's a pure fantasy, a thought experiment. It's a process so perfect that you could run it forwards and then backwards, and the entire universe would snap back to its exact starting point. No waste heat, no friction, not a single atom out of place. Now, of course, this can't actually exist, but as you'll see, it's an incredibly useful idea. So what would you need to actually achieve this kind of theoretical perfection? Well, two completely impossible things. First, the process would have to be what's called quasi-static, which is a fancy way of saying it happens infinitely slowly. Like, imagine compressing a gas by moving a piston one atom's width every million years. Second, it would have to be non-dissipative. That means a world with zero friction, zero air resistance, basically zero energy loss of any kind. Since we live in a world where time actually passes and friction is very real, this perfect process is just a beautiful idea.
And that's a totally fair question. If this perfect process can never ever happen, why on earth do scientists and engineers spend so much time on it? Is it just a game? Not at all. The whole point of this impossible ideal is that it gives us a target. It's a perfect, unmoving goalpost. And the answer is right here on this chart. It's so important. The ideal reversible process sets the benchmark. It defines the absolute ceiling for efficiency. A perfect reversible engine tells us the absolute maximum performance you can possibly get between two temperatures. Every real engine we build, whether it's in a car or a power plant, will always be less efficient than this ideal limit because of all those real-world messy effects. So this ideal process isn't a blueprint to build, it's the undisputed speed limit of thermodynamics.
Okay, so let's pull all this together and look at the big picture. When you put the first and second laws next to each other, you see they're not really talking about the same thing at all. They're giving us two different but equally important pieces of the puzzle, the quantity of energy and the quality of energy.
This is such a great way to visualize it. The first law is all about quantity. It's like a bank account with a fixed amount of money in it. The total amount of energy is always conserved. The scales are always balanced. But the second law is about quality. It tells us that every time you do something real, the quality or the usefulness of that energy goes down. The battery runs down. The organized useful energy gets degraded into disorganized useless heat. And this steady increase in disorder has a name. We call it entropy.
So let's wrap it all up. The second law gives time its arrow, because real processes just don't run in reverse. It tells us that heat always flows from hot to cold on its own. It makes it clear that a 100% efficient engine is an impossibility. It reveals that the universe as a whole is always moving toward a state of greater disorder or entropy. And, maybe most importantly for us, it defines the absolute theoretical limits for anything we could ever hope to build.
And that leaves us with this really powerful final thought. The second law of thermodynamics isn't some guideline you can try to find a loophole in. It is a fundamental property of reality itself. The great challenge for all of science and engineering isn't to try and break this law, but to understand it so well that we can design our technology to be as clever and efficient as possible, right up to the very edge of that absolute unshakable limit.